My goal in this video is to tell you about some of the different models that climate scientists used and to tell you about some of the advantages and disadvantages of those climatological models. So this turns out the simplest climate model that scientists use is actually a model we've already seen. You may remember this from that reading that we briefly did in class. Essentially, these are just mathematical equations for black body radiation, and if you use these models, what you end up with is a value for the temperature on Earth. And so this value down here, um, assuming that there's no greenhouse gases, is really just a really simple climatological model of the Earth. There's not really a name for this, but it's just, sort of assuming that the Earth doesn't have anything on it except radiating as a black body. So obviously this is really inaccurate, and scientists don't really use this as a real climate model except as a starting basis. The models that we've seen in class are actually called box models. The reason they're called box models is that we're just assuming that everything is a set of interconnected boxes that's having fluxes, inputs, and outputs in different reservoirs. As we've seen, it works somewhat well in noticing how different variables will affect reservoirs and affect outside parameters like temperature, CO2. But it's a pretty coarse model. So instead of, we just talk about the atmosphere as a whole. There's no more sort of, we can't differentiate different layers of the atmosphere. We just talk about surface as a whole. We don't talk about the difference between mountains and deserts or polar regions and tropical regions. And so as a result of this sort of gross generalization or gross simplification, it's not so good for predicting things into the future, predicting impacts of CO2 change with any sort of accuracy. So instead, scientists don't rely just on box models, and they use more complicated models in which you break out the Earth into these different regions. So a simple zoned model just looks at differences based on latitude. So, these different zones in here will receive different amounts of radiation. That's what is sort of being shown over here by these obscure Greek symbols. And then they'll receive different amounts of radiation, radiate different amounts of radiation, and thus have different temperatures. So here's a model. Let's actually run this model. It's super, super simple. So you can tell, looking at it, here's the number of iterations or number of sort of different runs we're going to do. You can put in different values for things like albedo, radiation loss, ice albedo, blah, blah, blah. These things aren't that interesting. And interestingly, you can put in different values for the different zones. Again, remember the zones were different bands away from the tropics. So you can put in radiation and their starting temp. In any case, you run the thing, and it plots the global temperature for these different zones. Okay, so it's, again, sort of getting a little bit more complicated, a little more sophisticated. Still not very sophisticated because it assumes that everything in that zone is the same, and it actually doesn't differentiate oceans and land. So here's the real deal, a global climate model, or a GCM. Why this is a real deal is the following. What we do is we break up the entire Earth into these different units. So you can see each latitude, longitude region has a different little unit. And so we can focus on one of these little boxes and thus get a much better idea of what's actually going in on this box. But we don't just focus on the box in 2 dimensions, we actually build models 3-dimensionally too, to show what's going on in this part of the atmosphere versus this part of the atmosphere. So as a result of this, there's a tremendous number of different units that we have to analyze. One of these big local climate model systems can have, 100,000 different units on the Earth at one time. And here's the kicker. We need to not only represent what's going on in each of these units, we need to do that over many, 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 many time units in order to get a good prediction or simulation of what's happening climatologically. And we don't need to just focus on this one unit. We need to also look at how that unit is linking with its neighbor down here, right? So in other words, with all the different processes that we've seen, how heat is being transferred between the ocean and the air, how solar radiation is interacting, how advection, meaning the movement of heat through currents, is happening either in the atmosphere or in the ocean. Here's sort of another way of thinking about this. So here's these different cells that we were talking about, right? So this is becoming an insane box, but wow, that was supposed to be a box. My daughter would be proud. Anyway, there's boxes, and so they're transferring heat vertically, laterally between mountains and land. You actually, interestingly, you'll love this. You have to figure out the specific heat capacity of different things in order to see how easily land versus oceans versus air will give up heat to one another. So you can sort of get the idea that rapidly this becomes insane. We're not, this is probably good news for you, we're not going to do any of the details of modeling these global climate models, GCMs. Instead, we're just going to look at their results. So you obviously need a hell of a powerful computer in order to do this, because you're modeling hundreds of thousands of these different units, looking at how each single one is transferring heat back and forth between one another, and you're doing this over, it can be as many as 1 million different runs in order to realistically predict how the Earth is transferring heat and acting over a long period of time. You need supercomputers or a distributed computer network to do this. One way that we check to see how accurate these models are is we plug in previous data into them. So you can see on the x-axis here, there's climatological data for the last 100 years. And so the black are these climatological observations. By the way, the reason that there's some dips is that these things here are volcanoes, and volcanoes produce tremendous amount of small aerosol particles into the air, and thus if you look at a big volcano like Pinatubo in the Philippines, and what was that, 1991 or something, there's a big dip in the global temperature. So black is, again, observations, and this massive yellow lines are the results of, like it says over here, 58 different models, different climatological GCM models. The red line is sort of their average of all of the 58 different results. And you can see that it does pretty well in lining up with the actual black observations. There's some issues here probably, and it's not so hot in there, but from 1960 on, it's pretty darn accurate. So that's how you check the accuracy of your model, is you use actual climatological data from the past and see how well it lines up. Of course, this is assuming that you have good climate data from 1900, which is an interesting question. It turns out we have really good data from about 1940 on, but before then it starts to get a little bit more sketchy. And so there's many ways that people have tried to check the actual data record and see how accurate it is. Anyway, once you're confident that your model is more or less lining up with historical data, what you then do is you run it into the future and you predict what's going to happen. So here's the deal. This is the prediction about 90 years from now, 80 years from now, versus the average from these 30 years, 1960 to 1990, and looking at temperature change. In the future, it's all increasing. So the result is that we get tremendous amounts of warming in polar regions, and well, really, that's the primary area of warming. Also, some significant warming in the Amazon basin and in sort of the central Russian steppes. We can do the same thing not only so that this is for one model based on this model named on here. You can see that if you run multiple models, you'll get slightly different results. So 2000, I think, is the starting point for this, so 0 in other words. And what they did is they ran the model back in time for these different things and see how well they lined up. And then they start to diverge in the future because each model has slightly different sets of assumptions or does different things better or worse. And that's why they diverge in the future. Interestingly, when it comes to future predictions, you have issues not only in how well the model is predicting what's going to happen in the future, but you also have to predict what humans are going to do in the future, right? So in the last global IPCC report, International Panel on Climate Change report, they came up with 4 basic scenarios for what people will do. And so here's sort of a depiction of those scenarios. One idea was that people would be focused on economics. They had another set of scenarios where people were more environmental, and then they had one scenario where the world became more and more globalized, homogenous, like you can see. One more focused more on regional differences, and it was a more diverse world, heterogeneous world. So depending on which of these different scenarios you do, you end up with big differences in climate change. Unsurprisingly, if it's a globalized, economically focused world, you get the biggest possible, rise in CO2. Also, perhaps unsurprisingly, if it's environmentally focused, you get smaller rises in CO2. So this is a little bit of a background about the science behind these models and also how we can use them for predicting